Good morning, everyone. Myself, Nirdesh Singh, corresponding author of the manuscript with the reference number 21314, entitled Energy Storage Participation for Frequency Regulation of Microgrid in PV-Dominated Power System. This manuscript has been recently accepted in International Journal of Applied Power Engineering. Now I'm going to discuss some highlights of the paper to fulfill the general requirements. So now I'm sharing this presentation. This is the title of the paper, Energy Storage Participation for Frequency Regulation of Microgrid in PV-Dominated Power System. This is the table of content, what content we are going to discuss in the presentation. Now, our topic is related to two terms, actually three terms: energy storage system, microgrids, and PV-dominated power system. First of all, we must know what microgrid is. A microgrid constitutes a cluster of interlinked loads and distributed energy resources delineated by distinct electrical boundaries functioning as a unified controllable unit to the grid. Microgrid can work in both the modes, that is grid connected mode or isolated mode. This figure shows the pictorial representation of microgrid. As we can see in the picture, this is basically the system that we have taken in our study. Our microgrid consists of PV system and battery storage system, and this system is connected to the grid. Some of the key features of microgrids are decentralized energy systems offering enhanced reliability by reducing dependence on the main grid. Because this can be worked in both the modes, that is autonomous mode also. So it reduces the dependency on the main grid. Second one is resilience. They can operate in islanded mode and the same thing. Efficiency. Microgrid reduce transmission losses because microgrids are generally located near the load. So transmission lines, the length of transmission line reduces, and hence the losses are also reduced because of the reduction in the resistance. Some components of microgrids are energy generation, energy storage, and control system. Microgrid integrate various energy sources like solar panel, wind energy, diesel, heat, combined heat and power systems, or hydro, fuel cells. Many of the renewable sources can be connected in the microgrid. Energy storage is also essential part of the microgrid because energy storage makes the balance between supply and demand. Control system, advanced control system manage the distribution of energy, balancing supply and demand, and switching between grid connected and islanded modes. Now, what is PV dominated power system? PV dominated power systems are electrical grids or microgrids where photovoltaic solar panel are the primary sources of energy generation, means the penetration of the PV system is high. And use of PV system is basically coming with the decline in the cost of solar panels and advancements in energy storage. Some characteristics of PV dominated power systems are high penetration of solar PV, obviously, because we are using PV dominated itself reflects the penetration of PV systems. Intermittency, solar generation is variable and dependent on weather and time of day, requiring sophisticated energy management system and storage solutions to ensure a stable power supply. Next is grid integration challenges. Of course, we have to face some challenges when we connect the PV system with the main grid, and it will require the stability of the grid, advanced forecasting, grid management, and potentially grid upgrades. We have some benefits of integrating microgrids with pin-dominated system, out of which some are sustainability, energy independence, and cost. These are the main advantages of integrating PV systems with the main grid. These three we have also discussed in the previous slides, how the cost reduces and how the independency reduces. Okay. Next is, because we have some benefits, so we have to have some challenges also in integrating the microgrids with PV dominated system. And some challenges are balancing supply and demand, technical complexity. Integrating high levels of solar PV requires sophisticated control system to ensure reliability and stability. Regulatory and market issues. The growth of microgrids and PV dominated systems often requires changes in regulatory frameworks and market structures to accommodate decentralized and renewable energy generation. Now, what is the importance of frequency regulation and why do we need the frequency regulation? Frequency regulation, or we can say frequency, is a crucial aspect in maintaining the stability of the system, because frequency reflects the change in frequency reflects the imbalance between the power supply and power demand. In electrical grid, frequency must be kept in a narrow range. It depends upon the region in which region we are using frequency, like 50 hertz or 60 hertz. But the variation of the frequency must be plus minus of 1%. Now, the need of frequency regulation is grid stability, because we need we want the grid to be stable. So to make the grid stable, we have to stable the frequency. We have to make the frequency within a range. Protection of equipments, because the variation of frequency may damage the equipments. If basically variation of frequency depends upon the variation of load and variation of generation. Like if load is reduced, the frequency will increase, and if the load increased, the frequency will be reduced. All the devices are designed to operate within a specific frequency range. Significant deviations can cause malfunctions, overheating, or even damage to sensitive equipments like motors, transformers, and generators. And all these equipments are very important for the power system. So, these equipments, not only these equipments, all the equipments must be safe. Synchronization of power sources. In interconnected power system, multiple generators need to work together. If the generators are not synchronized, it can lead to disruptive power surges and oscillations, potentially damaging the infrastructure. Maintaining power quality. Power quality means the frequency and the voltage of the system must be rely in a particular range. Poor frequency control can lead to voltage fluctuations and harmonics, which degrade power quality and can impact the performance of lifespan of electrical devices. Some conventional method of frequency regulations are primary frequency control, secondary frequency control, and tertiary frequency control. In primary frequency control, loop control is used. In secondary frequency control, automatic generation control is used. And in tertiary frequency control, economic dispatch is used. But apart from all these three conventional methods, we are not using these conventional methods. We are using energy storage system for the regulation of the frequency. So while we use energy storage systems for frequency regulations, what challenges we have to face? Some of the challenges are integration of renewable energy, declining system inertia, more renewable energy sources replace conventional thermal power plants, so the overall inertia of the grid decreases, decentralization of power generation. With the rise of microgrids, the centralized control of frequency becomes more complex. So now we will go to the energy storage system. What energy storage system is and how energy storage system works for the frequency regulation. Energy storage system is basically a technology that stores energy for later use. Means if the load demand is low, surplus energy will be stored to the energy storage system, and when the demand is high, this stored energy can be used for the lightning, electricity purpose. ESS plays a crucial role in balancing supply. Some key functions of an energy storage systems are energy balancing. It makes the balance between supply and demand. Grid stability. As there will be balance between supply and demand, so grid will be stable. Renewable energy integration. In integration, it works because it uses we can use surplus energy or deficit of energy at the same time. So integration will be easier. It works as a backup power. It works for peak shaving, load shifting, and demand response also. Some components of energy storage systems are storage medium, in which the energy will be stored, power converter system. In some of the applications, we need AC energy. So, our converter system from DC to AC will be required. Energy management system, the control system that optimizes the charging and discharging of the ESS, and monitoring and control system, sensors and softwares that monitor the performance and status of the ESS, ensuring safe and efficient. Now we will go to the types of energy storage system. In general, we have four types of energy storage systems. First one is electrochemical, mechanical energy storage, electrical energy storage, and thermal energy storage. In electrochemical energy storage, we have storages like flow batteries or hydrogen. In mechanical, we have flywheels and compressed air. In electrical, capacitors, supercapacitors, and superconductive magnetic materials are used. And in thermal energy storage systems, hot water storage, thermal fluid storage, ceramic thermal storage are used. So now we must know how the ESS supports frequency regulation, how the ESS does the frequency regulation, how the frequency becomes controlled while we are using energy storage systems. First step for the ESS to support the frequency regulation will be a rapid response to frequency regulation. It will recognize the deviations of the frequency and consequently will respond to the to make the balance for frequency. Unlike traditional power plants, which may take several minutes to adjust their outputs, the speed of ESS is in milliseconds. ESS respond within milliseconds, while there is a deflection of the frequency. Next is absorbing excess energy, that is frequency drop. When the grid frequency rises above the nominal value, it indicates that there is more power being generated than usual. In this case, the ESS absorbs the excess energy by charging its storage medium, whatever the medium is. This reduces the amount of power flowing into the grid, helping to bring the frequency back down to its normal range. So, in this manner, the frequency can be regulated. Next one is releasing stored energy. When the grid frequency drops below the nominal value, it indicates that power demand is exceeding supply. It's the opposite condition than previous condition. In this case, the ESS can quickly discharge stored energy into the grid, increasing the available power and helping to raise the frequency back to its target level. Yeah, target level. Next, it works for the grid stabilization. How it works for the grid stabilization? ESS can provide continuous real-time frequency regulation by dynamically adjusting its output based on the grid conditions. ESS can participate in both primary and secondary frequency control, offering flexibility in grid management, supporting renewable integration. Last but not the least, that how can the frequency can be regulated with the help of the energy storage system. Apart from frequency regulations, ESS also works for different or various types of ancillary services. Some of the ancillary services are bulk energy, that is energy arbitrage or peak shaving. It can be used for the load following, voltage support, black start, frequency regulation, spinning reserve, customer energy management, that is to maintain the power quality, power reliability, renewable capacity firming, and renewable energy time shift also. These are some of the ancillary services that can be achieved with the help of energy storage system. Benefits of using ESS for frequency regulation. Some of the benefits are it increases grid stability, it enhances the renewable integration that we have discussed in the previous slide. Cost saving is also a important part, and lower emissions. Lower emissions means by reducing reliance on the fossil fuel-based power plants, ESS help decreases greenhouse gas emissions. This is the principle of control, what we are using in our study. This is a grid, solar PV, three-phase load. And this system is used for the frequency regulation in our table. These are some results. Here we can see two pictures. In one picture, there is a frequency at load bus without any controller. And in one picture, there is a frequency at load bus with controller. When the frequency at bus without controller we are using, there is a jerk or high jerk in frequency. It may go from 59.7 to 60.3. Or when we are using the controller, the frequency become constant to almost 60 hertz level. So we can see from the figures that in figure 1, following a 20-second simulation, we are using 12-second simulation here. And in this simulation, the frequency drops 59.68, 59.80 and 59.77 hertz at 0.53 and 4.5 seconds. These three periods or instants are the instants where the load is changing. In addition to the existing load is 100 kilowatt, and we are reducing the load by 50 kilowatt, then 30 kilowatt, and then again 50 kilowatt. At 4.5 seconds, battery begins discharging at 50 kilowatt to meet the heightened demand, resulting in a frequency declining to 59.75. Whereas in second figure, where we have used the controllers, this is also the simulation for 12 seconds. Initial frequency decreases to 59.68, and at 5 seconds, attributed to additional load of 50 kilowatt. Subsequent drop of occurs at 3 seconds, resulting in a further load increase of 30 kilowatt. So subsequently, the frequency stabilizes at 59.9. This was all about the results of our study, and the conclusion is maintaining a balance between active power production and consumption stands as a pivotal factor in guaranteeing frequency stability within the microgrid systems. These are some references. So this was all about my presentation for this study. Thank you so much. Thank you.